In this video, I would like to build over the one-dimension heat conduction problem that we used in multiple recording, looking for how to apply the backward finite difference method. Then we use the central finite difference method, and then we explain how to use the different iterative techniques or schemes like Jacobi and Gauss-Seidel to solve the system of linear equation. I will take you here through another example, very, very typical to what we did before, but I will change one of the boundary conditions to show that sometimes finite difference method need more additional tool to be able to help you solve that problem. So let's assume that we are having the same one-dimension bar, and we still have the same Dirichlet boundary condition. So the temperature is 100 degrees C, and the face has a temperature of 20 degrees C. The total length is still 0.6 meter. The thermal conductivity of the bar is 10 watt per meter Kelvin. And I would like to get, I will do some changes here. That's the original example. I would like to do some change. What I'm going to do is I will eliminate that phase temperature boundary condition. I will just say that that phase is no longer at 20 degrees. It's exposed to a fluid flow, a convection, at a T infinity of 20 and given heat transfer coefficient. So this is the original design. This is my new or modified design here. So I will have 100 degrees at that phase. Now the lengths remain the same, thermal conductivity remain the same, but now this phase is no longer at 20 degrees, but I'm exposing that phase to a fluid at 20 degrees C and convection heat transfer coefficient of 10 watt per meter square Kelvin. So that the right boundary is exposed to a fluid flow. And I would like to get the temperature distribution along that bar. So again, that's my design. I'm not going to change that. Number two, so the design here is no change, right? Just the boundary condition change it, but it's still one-dimension heat conduction problem, and the boundary condition is exposed to a convection. Number two, what's the governing model? Again, I would like to get the temperature distribution within the bar, so I'm still in the Laplace equation. With the assumption that it's one-dimension, steady state, no internal source of heat generation, I'm going to end up to have Laplace equation starting from the heat diffusion equation. Then boundary condition is changed, right? The boundary condition changed. So at x equals 0, I was given the temperature that's equal 100 degrees C. Now at x equal L, it's no longer constant temperature. I will get back to that and match the different type of boundary condition recording part when we introduce the Dirichlet, Newman, Mixed, Cauchy, and the other stuff. But let's think in a simple way now. Okay, what I'm going to do, I'm going to do the discretization. I'm not going to solve that with the analytical solution. I will do the discretization. So I'm going to use central finite difference method here. I will use the central finite difference method. So I'm going to need the, remember, this is the second derivative of the temperature relative to x is equal to 0. So that's my governing equation here. So I'm going to need the second derivative, f double prime is equal to f of x plus h minus 2 f of x plus f of x minus h divided by h squared. That's the approximation of the second derivative, which can be written as partial t by partial x, partial 2t by partial x squared for a given point I is t. Now the function's temperature, I plus 1 minus 2 ti plus t I minus 1 divided by delta x squared or h squared, whatever you like to call. So that's the equation. Then I have the second derivative is equal to 0. So delta x squared is gone. So at any node, I can apply the numerator of the equation. So the next step, I'm gonna actually do the gridding, right? So I'm gonna break down my domain into the pieces here. I'm gonna stick to the same delta x equal 0.1, like what we did with the previous example here. So I'm gonna note this node 1, node 2, node 3, node 4, and node 5. Now remember, this node here, it's unknown temperature too. I don't know what's the temperature here. I know what's the exposed fluid temperature is, but I will call that node 0. Now we added another unknown here. So if you use the central finite difference method here, I will need node to the right, node to the left, and twice the node of interest or the base point equal to 0, right? That's what this equation says. So for example, if I want to apply for node 5, I will bring them backward. So node 5, the equation will be actually T4 minus 2T5 plus 100 equals 0. If I want to go for node number 4, so the equation will be T5 or T3 minus 2T4 plus T5 is equal 0. If I want to go for node number 3, it will be T2 minus 2 of T3 plus T4 is equal to 0. If I want to go for node number 2, it will be T1 minus 2 T2 plus T3 is equal 0. Then when I go for node number 1, it will be T0 plus minus 2 T1 plus T2, just to keep the order, equal 0. Now, 1, 2, 3, 4, 5 equations, but now I have 6 unknowns. So I need another equation for node number 0. If you apply the central finite difference method for node number 0, you're going to need node to the right. Like every other node here, you need 1 to the right, 1 to the left. So T3 plus T5 minus 2T4, that's the equation. Now, if you apply that for node 0, I have T1, but I don't have anything to the right. And you cannot have established a node on nowhere. It's outside your domain, right? So there was a motivation to look into more, deeper into node number 0. So let's look to node number 0 here, then how we can treat that. Then to be able to drive an equation for node number 0, there is an easy way, but there is another way that I would like to share with you guys. It's a different method that we can use. It's called the energy balance method. This is sometimes it's very helpful method to get you extra equation for a node. And by the way, the results you are getting from the energy balance method should be very consistent with what we are doing here. But let's explain what the energy balance method looks like and how you apply that to get extra equation for node number 0. And I will apply that to any of the other node too. When we establish that method, you can apply to any other node and you'll get the same equation exactly. I will show you that further down here. So let's look to the energy balance method. So the energy balance method, if you go back and refresh your memory with the fundamentals of heat transfer course, you'll find that the total energy coming into a system plus the total energy generated within that system should equal to the total energy out plus total energy stored. So if you have a system, this system is receiving energy, we call the energy in, internally generating energy generated. Then now this is the saving of total energy into that body. He may store something, so there is energy stored, and he will reject some of that energy out. So the relation that tie between all of them is the total energy in plus the energy generated. This is the gained energy equal whatever is stored and plus whatever is rejected out. Sometimes when you refer to the heat transfer book, you'll find that there is dot here, there is dot here, there is dot here, there is dot here. It's all energy transfer to be of the unit of watts all the time. Now, so this is total energy supplied or energy enters. And this is the energy actually get out of your body. This is the generated energy. Again, each one of these has a unit of watts. And we mentioned in previous example about the Q dot, which is known as the volumetric heat generation or the heat generation source. Q dot usually comes with the unit of watt per meter cube. That's why we call that volumetric heat generation. So if you want to create actually E dot G out of the Q dot, the simple relationship that E dot G, the capital one that has unit of watts, should equal to Q dot times the volume of your body, right? So that's watt per meter cube times meter cube. You end up having the homogeneous units or dimension for both sides of the equation, correct? Then the energy stored is, if you guys recall from the middle school relationship, that energy stored is actually equal MC delta T. And mass can be calculated from rho density times the volume. So that's density of the body times the volume of the body. Now this is completely give you the mass. C now stands for CP, that's a specific heat. Now, since we are not dealing all the time with a steady state condition, so this will be actually partial T by partial time T. Instead of delta T, it is a variation of the temperature relative to the time. We call that temperature time gradient. So that's the general form of stored energy. And remember, if we are solving steady state for steady state, anything change with time is equal to 0, right? So this will equal 0. Partial T by partial time T will equal 0. But this is a general feature or the general definition of each term into that energy equation here. So can we apply the energy balance equation or energy balance method over the nodes that in the numerical technique? Yes, we can do that. This can apply for a big body or can actually apply for an element or control element. So we can apply the energy balance method over a control element. Here are the assumptions that we use all the time with the energy balance method. So I would say these are the assumptions, or these are the rules to use when you apply the energy balance method. Number one, we assume all energy are getting into your body. And between parentheses, I'm going to put here the control volume. So when you pick up a control volume, you assume all the energy is coming into it. Nothing is going out, okay? Again, number two, the Q dot is only occur or is Q dot generated within the body. And then instead of using the word body, I'm going to use control volume. Number three, the body or control volume always have a depth of unity, unless you're solving three-dimension problem, which is going to be complicated here. But these are the general assumptions that we use all the time to apply the energy balance method or technique. So let me explain that in a simple way so you can get the sensation how this equation applies. So let's assume that you have a wall and this is a boundary, this is a boundary. I have a node in here. I'm going to call this is node I. This is node I plus 1. and this is I minus 1, correct? Then I'm interested to find a formula or correlation for node number I. Using the energy balance method, then we can compare that with the finite differences. So if I'm using, again, let's do that here now. If I'm using the central finite difference method, what would be the equation for node I? Okay, if I'm doing the second derivative here, right? That's our concern all the time. The equation will be, looks like what? It's going to be Ti plus 1 minus 2 Ti plus Ti minus 1 equals 0. And this is what we did in the previous examples here all the time. So this is what we got for finite difference method for node I, second derivative equals 0, right? That's the Laplace equation. Now let's see how we can apply the energy balance method for the same node I, and we end up having the same equation. So here is a step. Number one, you need to create something called control volume. What's a control volume? Originally, when you look to that, we know that this distance here, this is delta x, or if you want to call the h and h, that's fine. Your control volume is the area of influence of the node I. And the influence of node I is zoned by a square, okay, by a square has a length of delta x. So what you're going to do, you're going to come around node I, you're going to draw a square. That's your control volume. And the dimension of this guy here is delta x times delta x. But here we are solving one dimension, so I don't need the second one. I'm looking only for the x direction, okay? So this is delta x, and this will go infinity because we are solving one dimension. But if I'm solving two-dimension problem, and there is node up here, there is node up here, I'm going to choose that delta y. But now let's stick to the one-dimension problem. Then, this is my control volume. I'm going to mark that. I'm going to write down here, that's my control volume. Okay, now, let's stick to this assumption here. Number one, we assume there are energy coming into that one. So, which means that the temperature of point I will be the lowest and the surrounding temperature will be higher, which means that node I plus 1 will have a higher temperature compared to node I, which means that there is energy will be supplied into that direction. I'm going to call that Q1. Node I minus 1 will have a higher value compared to, as a temperature compared to node I, so I will send energy down here. That's Q2. If we are solving two dimension, there will be heat coming into here, and there is heat coming into here. So that's assumption number one. All energy are getting into your body. Q1 is coming in, Q2 is coming in. Number two, heat generation is within your body. If there is Q dot, it will be only calculated by this control element. So if you want to get E generated, you need to multiply Q dot times the volume. This volume will be that volume here, and Q dot will be within here. But now this equation was based on no existence of any heat generation source. So I'm not going to include any heat generation in that part. So E generation will be 0 for that example here. Okay, so for that specific example here, we are solving here to match this equation. E generated is equal 0 because we didn't count for any internal source. Number two, we actually solve a steady state, so energy stored will be 0 because it's a steady state. So the energy equation, this equation, will end to be looks like that. It will be energy in equal to energy out. Energy generated is 0. Energy stored is 0. So the total energy in equal energy out. But we assume everything is coming in, so energy out also will be 0. So I'm going to end up having the total energy in equal to 0 for this specific case, right? So let's look to the energy in. I'm talking about energy into the control volume. We have two Qs, so the energy in has two values here. There's Q1 and Q2. Let's look to Q1. The heat going into that direction is going through a solid body, right? So Q1 is actually simply a conduction. And if you go back to Fourier's law in conduction, Q1 simply is K, the area that's perpendicular to the heat direction, times delta T over X, or delta T over L. This is Fourier's law, right? So let's apply Fourier's law for Q1. Okay, here's Q1 is going to equal to thermal conductivity of that body, that's a solid body, times the area, and the area has to be perpendicular to that Q1, which will be the height times the depth. Height is infinity, depth is 1, but it's going to cancel out in this case. But if we are solving two-dimension problem, you have to find your delta y, and the depth is 1. You can calculate your area. Now, you pick up delta T that drives that Q value. Delta T that drives that Q value is T I plus 1 minus Ti. Remember, heat is going inside that control volume or control element. So delta T over L, what's the definition of L? It is the same distance between these two nodes. So between this node and this node, the distance is delta X. Let's do Q2 now. Q2 is going to equal to K times the area, which is almost the same area. It's not almost, it's exactly the same area that's perpendicular to Q2. Same height, same depth. And now delta T, I will take Ti minus 1 minus Ti, and the distance between the two nodes here is actually delta X. Oh, stop. Why you didn't do Ti minus Ti? It's coming in. This higher temperature compared to this one, go back to the original assumption here. Okay? So let's get our total energy in. Energy in will be, you add up these two. I'm going to take K, it's the same thermal conductivity. A is a common area. Then I will take delta X as a common factor. What I'm going to end up having, Ti plus 1 minus Ti plus Ti minus 1 minus Ti. Let's actually collect the terms here. So it's Ka over delta X, Ti plus 1 minus 2 Ti plus Ti minus 1. Remember, the energy balance equation said that energy in plus energy generated equal energy out plus energy stored. 0 for steady state, 0 for the assumption of the energy balance method, 0 because there is no heat, internal heat source is assumed. So the energy in should equal to 0, right? This term has to equal to 0. So this term is the summation of these two. So I will have Ka. Now I don't think so we need this. I would keep it for comparison. So Ka over delta X times Ti plus 1 minus 2 Ti plus Ti minus 1. It's equal to 0. You cancel out this term. I'm going to end up having Ti plus 1 minus 2 Ti plus Ti minus 1 equals 0. If you look to this equation and the equation generated from the central finite difference method, you got exactly the same results. So this is how we apply the energy balance method, and we got exactly the same nodal temperature. So let's get back to the example and see how can we take advantage of the energy balance method. I'm getting back to this example here. I was able to secure multiple equations for all the nodes. I would like to deal with node number 0 here and see if the energy balance method will provide help here. Again, if you apply that energy balance method, same way for nodes 1, 2, 3, 4, 5, you end up having the same equation here. Now let's try to use that energy balance method for node number 0, because the central finite difference method failed to find a node next to it to the right? So we couldn't find a node outside here. So we're going to use the energy balance method to find an equation for node number 0. So let's do that here. So I will redraw the design or the model or the domain. I'm just going to scale it up. Remember, there was node 1 in here, and there is node 0 here, and there is T infinity in here, that's 20. And the value of H, I'm just collecting my given information, H is equal 10 watt per meter square Kelvin. Now I would like to get an equation for node number 0 using the energy balance method. Okay, step number 1, draw your control element. This is the distance here is delta X equal 0.1 meter. Number 1, pick your node, that's your I point, draw a control volume that's simply a square of the side length of delta X. Again, we are solving one dimension, so I'm gonna just draw the two sides of that square. Remember, that distance here is delta X. Okay? Now, this is on air. This does not exist. So actually, my control volume will be very simply that part. So that's not exist. Again, I cannot deal with something imaginary. I cannot imaginary looking into that part and say, oh, there is a hidden boundary condition I'm going to use here. Imaginary things is not going to help here. So I will stick to that side here, and this is becoming my control element now. Okay, now let's draw. After I draw the control element, I will draw all the energy coming into the element. So number 1, this is a solid body, right? So any transfer of energy into that solid body will be by conduction. Again, we're assuming that temperature is the lowest one because force every energy to come in from all directions. So I will have Q1 coming in from that direction. Now, there is a fluid up here. So that fluid will send some energy into the body here. I'm going to call that Q2. So I'm satisfying the first assumption that assuming all the energy are coming into that body. Now, what is the equation? Energy N plus energy generated equal to energy out plus energy stored. This is 0 for steady state. This is 0 for the assumption. This is 0 because we assume Q dot does not exist. Dot, 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 and dot. So I'm going to end up having energy in equal to 0. Now, let's actually break down the energy in. We have Q1. Q1 is a heat transfer through the solid body. Fourier's law, right? Q1 is equal K times the area perpendicular to that Q. So it's going to be the height times the depth. I'm going to call it A. I'm not going to change that. Times delta T over L. So it's K, A. I will pick delta T, that's T1 minus T0. And the distance between these two nodes is actually delta X. So that's Q1. Now, let's look to the Q2. Heat is going into, or energy is transferring to node 0 by a fluid. That's Newton's law of cooling. That's convection. Q2 is simply H, A, delta T. That's the equation of Newton's law. Newton's law of cooling. In a simple word, that's convection. So H is given. A is going to be that height times the depth, which is the same as the area here. So I'm going to keep it A. Now, to assume the energy is coming in, the fluid temperature is always assumed to be higher than the node temperature, T0. So T infinity minus T0. That's the equation for convection. Let's take that Q1 and Q2 and substitute into the equation. So I would have K, A, T1. Let's have delta X in here. Minus T0 plus H, A, T infinity minus T0 is equal to 0. A will cancel out. So I will have T1 minus T node. I will multiply by delta X over K here, delta X over K here. So I will have delta X over K multiplied by H. Later on, we're going to call that separate name, times T infinity. I will distribute that here. So I'm going to have delta X H over K T node is equal 0. I did that so I can collect the term here. So I'm going to have T1 minus 1 plus delta X H over K T0 plus delta X H over K T infinity is equal to 0. Remember, delta X is 0.1. H is given by 10 watt per meter square Kelvin. This is 0.1 meter. K is given in the problem by also 10, right? So, and T infinity is given by 20. So this will end up to be a number value. This will be a value. So you end up having the equation in two unknown, which is T node and T1, T0 and T1. So if you take that equation with the other equations, you will have your 6 unknowns in 6 equations. So let's substitute here. So T1 minus 1 plus delta X is 0.1, H is 10, and K is 10 times T node plus 0.1 times H is 10, K is 10 times 20 equals 0. 10 will cancel out, so I have T1 minus 1.1 T node plus this will give me 2 equals 0. And this is node 0 equation. Now you can list all these equations together and solve using the matrix method using MATLAB, or you solve by any one of the iterative methods. I will get the following here. So I'm gonna list all the equations here. So I will have node 0, node 1, node 2, node 3, node 4, node 5. These are the 5 equations. For node 0, I have T1 minus 1.1 T node plus 2 equal 0. For node number 1, I got T node minus 2 T1 plus T2 equal 0. Got T1 plus minus 2 T2 plus T3 is equal 0. I got T2 minus 2 T3 plus T4 is equal 0. I got here node 4, I got T3 minus 2 T4 plus T5 is equal 0. Then for the last node, I got T4 minus 2 T5 plus 100 equals 0. Remember, the order of the nodes is like this. That's node 0, node 1, node 2, node 3, node 4, node 5. And that surface is 100 degrees. And here I have a T infinity of equal 20. So what's your expectation of the temperature? Temperature has to go decrease all the way that way, right? This cannot be lower than any temperature here cannot be lower than 20 or cannot be higher than 100 since we don't have any energy stored or energy generated, okay? So you should be able to take these equations, you solve that by any method that you like to do, and you should be able to get the following. I got the following answer. T node is equal to 70. T1 is 75. T2 is actually 80. T3 is 85. T4 is 90. And T5 is 95. These are all in degree C. So this is 100, 95, 90, 85, 80, 75, 70, then the 20. Again, temperature seems to be linear within that body, right? And the convection outside. So this is how the energy balance method works. Finite difference method works great, right? But in some situation, we have to use the energy balance method. As soon as you add heat generation into the system, now you have to consider for that term, which is going to complicate the issue a little bit. But still, energy balance and finite difference method can be mixed and used all the time to solve that problem. Let me just highlight one thing here. If I look into node number 0 here, right? There is heat in reality in the application. There is heat coming by conduction here, right? And there is heat will leave by convection. That's the real application. Forget about the condition of the energy balance method. And that's true, 70 degree, 20 degree heat will leave, but to assume it's coming in, this is part of the assumption to use the energy balance method. So at the interface, at that interface, you are receiving heat by conduction and you are rejecting heat by convection. So how you calculate the conduction? Fourier's law minus K, A, partial T by partial X. And this conduction should equal the convection, which is HA delta T. You cancel the A, you can say that partial T by partial X is equal to minus H over K delta T, which means that partial T by partial X has a value here, right? It has a value. So this is explained that we don't have a Dirichlet boundary condition, right? We have a mixed boundary condition. We have a derivative somewhere at the one of the boundary, and we have a fixed value at one boundary. So this is not a Dirichlet boundary condition. I just want to show you how to reflect the convection interface to one of the 5 types of boundary condition that we discussed. So this is not a problem with Dirichlet boundary condition. This is a mixed boundary condition. Dirichlet at one side and Newman on the other side, because I have a value of the derivative here, partial T by partial X. So again, this conclude the importance of the energy balance method and how to use it, and you get the same results with the finite difference method. That conclude that method here, and we will see how to apply that in more complicated problem next exercises.